right now. So welcome everyone. It's a great pleasure to welcome Evan O'Connor from Stockholm University today. Let me tell you a little bit about Evan's background. He received his PhD in theoretical astrophysics from Caltech in 2012. And then he became a postdoc at the Canadian Institute of Astrophysics in Toronto from 2012 to 2014. Then he was a Hubble Fellow at North Carolina State University until 2017. And since 2017, he is at the Oskar Klein Center in Stockholm. So Evan is interested in relativistic astrophysical systems, quark-hadron supernova, neutron star mergers, and also gamma ray bursts. And he's in particular interested in the simulation of these objects with a focus on the microphysics and also observational features in terms of neutrinos and gravitational waves. And in today's talk, Evan will tell us something about quark-hadron supernova as laboratories for fundamental physics. Please, Evan, when you're ready.
Thanks. Yeah, thanks for the invitation and the opportunity to come and talk to you about my science. So here are my collaborators. The first group in Stockholm I'll talk about on the next slide. My other collaborators include Sean Couch at MSU, Mackenzie Warren, who is in North Carolina State University. Elsewhere in Sweden, Aaron O'Sullivan, who is in Uppsala, and Manny, who was a master's student with Aaron, and I'll talk about some of the work that they did. And then Luca, who is a PhD student at Notre Dame. So my group in Stockholm are these people here. Aurore is a PhD student working on neutrino interactions in supernova. Shuai and Andre are both two postdocs working in the Oskar Klein Center, focusing on, well, some of the stuff I'm going to talk about today. So nuclear equation of state and quark-hadron phase transitions and black hole formation. And then Oliver and Samuel are master students, and I'll talk about some of Oliver's work here as well. But most of what I'm going to show is, of course, the work from my collaborators and people in my group. So I just wanted to highlight them. Supernovae in general have a really broad connection to the wider astronomy and astrophysics that a lot of people study. So quark-collapse supernovae come from massive stars. So we're talking about stars kind of up here on the main sequence. So more than about 10 solar masses. There are O and B type stars, so bright, hot stars on the main sequence, but then they become supergiants at the end of their life. This is when most stars explode, when they're red supergiants, so stars like Betelgeuse. And so studying supernova allows us to probe massive stars. And for many nearby supernova, we can actually go to pre-explosion images and see the star and understand what it looked like before it blew up. And this gives us a really good handle on stellar evolution, or a way to test stellar evolution. Quark-collapse supernovae, a particular subtype, type 1bc or type 1c broadline supernova, are associated with long gamma ray bursts. And so something is probably happening a little different in the core than the garden variety supernova that I'll talk about today that launches this gamma ray burst, but there is that connection to high energy astrophysics there. And all the neutron stars and black holes in the universe, or not the supermassive black holes, but the stellar mass black holes and neutron stars in the universe come from quark-collapse supernova. So whether the explosion is successful or fails, or a combination of those determines what the final remnant is, a neutron star or black hole. And LIGO, for example, is detecting many mergers of these objects, and that also is very much related to the science of supernova and vice versa, of course. On a much larger scale, supernova of quark-collapse type, but also type 1a supernova, play a big role in galactic evolution. So they inject energy into the interstellar medium, and they drive outflows from galaxies. That's what you're seeing here in the red. They trigger star formation, but they also inhibit star formation. So they're very complex role they play in galactic evolution in terms of the energy. But that really dwarfs the energy that they inject into the interstellar medium is really very small compared to the total energy released. And most of it is released in neutrinos. And this gives us a probe of particle physics and the high density physics happening in the center. These are the neutrino events detected in 1987A, or detected on Earth from supernova 1987A. Type 1a supernova, which are not quark-collapse supernova, but a different type of supernova that are a little bit brighter than the quark-collapse variety supernova, but of the same magnitude and so have the same name, are really important in cosmology because they help us understand the expansion of the universe and the physics that's happening in the universe at really early times because they're so bright and we can see them so far away. And supernova of both types contribute a lot of the elements that are on the periodic table. So here the red elements are elements that are predominantly formed in massive stars or in the explosion itself and then spread throughout the galaxy from the explosion. Gray elements are from type 1a supernova. And then purple elements are from, or we think, of course, everything is on error bars on here, but the purple ones are our process elements, which we think come from the merging of neutron stars. And again, those neutron stars come from quark-collapse supernova. So supernova have, a strong role to play in all the elements that, or a lot of the elements that we have in the universe. And then finally, and what I'm kind of going to focus a little bit on today is supernovae provide this excellent laboratory for studying extreme physics at extreme densities and temperatures and neutron to proton ratios. And so things like neutron stars, magnetars, black holes, they offer this great laboratory. And so today I'm going to talk about first some basics of quark-collapse supernova, and then I'll talk about two of these fundamental physics aspects that I just mentioned. So particularly looking a little bit at hadron quark phase transitions in supernova, and then some talk about the effects of the nuclear equation of state on supernova. And then I would like to talk about using, neutrinos can tell us a lot about a supernova. I want to look at one particular aspect as using them as messengers of the supernova itself. And then if there's time at the end, I want to just talk about parameterized explosion models for quark-collapse supernova. Okay, so supernova quark-collapse supernova come from massive stars. And this is an example of a massive star. It's 25 solar masses when it starts its life. And it burns through the hydrogen and then the helium and carbon all the way up to forming iron in the core. The timescales for those are kind of shown here for this 25 solar mass star. Most of the time is spent burning hydrogen, 10% or so is spent burning helium, and then the rest of the burning happens essentially instantaneously compared to the life of the star. So burning those heavier and heavier elements, you get less and less return for your work in terms of energy release when you make these heavier elements. And they're also cooling by neutrinos. And so the efficiency of the energy released is much lower. And then ultimately, when you get to iron, there's no benefit to burning it any further. And so you can't burn it any further, and you just build up an iron core in the center that's supported by electron degeneracy pressure. So there's not really any radiation heat that can support the star. It's mostly by electron degeneracy pressure in the core. And just like a white dwarf, there's a maximum mass that core can be before it will collapse in on itself. And so once you burn enough silicon to iron that builds up the core to a particular mass, the core will collapse. And so there's other factors in there too, like electron captures on the iron group nuclei, reducing the total number of electrons, which reduces the pressure as well. But in to zeroth order, once the core gets too big, it'll collapse. And this collapse is really in the very center of the star. So for a star like Betelgeuse, it's only a millionth of the star's radius, the iron core, when it collapses. And it will ultimately make a neutron star or a black hole, but if it makes a neutron star, a huge amount of energy is released. So 300 times 10 to the 51 ergs of energy is released. That mostly is radiated neutrinos, but some of that energy goes into the photons we see in these supernova, and then also unbinding the rest of the star and ejecting it into the galaxy. Okay, so now the core has started to collapse, so it starts off at densities of around 10 to the 9 grams per cubic centimeter or so. When it gets to 10 to the 12 grams per cubic centimeter, and so for reference, 10 to the 14 grams is nuclear densities, and so we'll get there in a second. But at 10 to the 12, the core kind of separates into outer part of the star that's supersonic. So the inflowing material is traveling supersonically. And also kind of at this density is when neutrinos that are being produced start to become trapped. So the capacity for the neutrinos is high enough that that they can't escape. They start to get trapped in the matter. That's about 5 milliseconds before what we call bounce, which is when the matter gets to about a few times 10 to the 14 grams per cubic centimeter. Before everything is collapsing in, and when it gets to nuclear densities, of course, you start to feel the nuclear force between the nucleons. And this is a force that can supply a pressure that can help the star maintain hydrostatic equilibrium. And so that new equilibrium is reached, but then overshot because of the infalling material. And it rebounds, this is what we call the bounce, and it rebounds, sends out a pressure wave, which steepens into a shock wave, and that's the supernova shock that will ultimately, for a successful supernova, unbind the whole star. And that happens at t equals 0, was what I call t equals 0, and when the densities get to about 10 to the 14. That shock does a couple things. One thing is it's dissociating all the material that flows through it. So the iron of the rest of the iron core and the silicon that's falling in breaks up into neutrons and protons. And that actually is quite an energetically expensive process. So the star spent its whole life making this iron, breaking it up into neutrons and protons again takes a lot of energy. It takes a good fraction, 30% of the kinetic energy that the nuclei have when they're infalling, but 30% of that kinetic energy just goes into breaking it up into neutrons and protons. And this taking away of energy from putting it into internal energy rather than putting it into heat causes the pressure behind the shock to not be able to overcome the ram pressure of the material outside. So this stuff outside is falling in really fast. It's holding down the shock. Interior to the shock, it's hot, and that pressure wants to push the shock out, but it's not hot enough to do it. The pressure isn't high enough, and so the shock stalls. This is the problem, the core collapse supernova problem, that we need to get that shock revived in order to actually cause an explosion, in order to send the shock out to large radii. And the prevailing mechanism that we think is responsible for this is the turbulence-aided neutrino mechanism. So this is when neutrinos coming from this blue region here, this cooling region, stream out into this red region and interact on some free neutrons and protons. So for example, an electron antineutrino comes out here, is absorbed onto this proton, converts it into a neutron and an electron, and the energy of that neutrino then gets ejected into this material. And so the red region is literally material where the energy is increasing because it's absorbing more neutrinos than it's emitting. So that's called the heating region or the gain region. And that increase, that absorption of energy, in addition to the pressure support from turbulence, this material here is turbulent, seems to be enough in many situations in order to allow us to successfully reproduce explosions that we see in nature. So it's very successful in 2D, and it's also successful in 3 dimensions too, although there's kind of fewer simulations available for that. And I'll show a couple of those next. But first, the movie, I guess. Here you'll see this turbulence developing and the shock kind of evolving. So the shock is the cyan region, the protoneutron star is in the core, and the convective turbulent motion of the material is this neutrino mechanism. In this model, it's not successful in blowing up the star. And so the shock just stays down here at a couple of 100 kilometers. But there's lots of other interesting and fun hydrodynamic stuff happening in this simulation as well, but no explosion. Right, so one of the things that, so these simulations are very complex and they have a lot of physics involved in them. And one of the things we wanted to do recently was make sure that of all the groups out there, there's 6 different codes here. Of all the groups out there studying quark-club supernovae, we wanted to see if we would get the same result if we simulated the same thing. And so we got together, carefully controlled the input physics and the initial conditions to make sure we were all doing the same problem, each with our completely independent codes, to see how well we could do. And I think we did quite well. So this is the shock radius, so the supernova shock. It's formed here at t equals 0. It goes out and it stalls, and then it starts to come back. These are all spherically symmetric simulations, so there's no explosion. So the shock just comes back and fails. But all the shock radii evolutions agree very well between these 6 different codes. And also the neutrino properties. So this is the electron neutrino luminosity. This is the neutronization burst that goes off the top of the page. And the anti-neutrinos, so the dashed dotted lines here. So right here at this peak, most of these codes agree within a few percentage points of each other in predicting what the luminosity is. Again, completely independent codes, but very carefully controlled input physics. So I think this is a very good demonstration that when we simulate the same thing, we get the same results. And then 2 of these codes recently have predicted, or at least 2 of these codes have recently predicted successful explosions in 3 dimensions. So with modern neutrino physics, modern codes, no symmetries, so full 3D. This is one example of them from the Princeton group of 14 simulations, and 11 of them are successfully blowing up. So this is the shock radius that is blowing up within a few 100 milliseconds of bounce. Some of them fail, so some of them are not successfully exploded, but many of them are. And this is a simulation from the Grushin group of one progenitor that was evolved 7 minutes before the point of collapse. So a 3D progenitor evolution, and then for 7 seconds after collapse. So again, the shock goes out, stalls, recedes a bit, and then gets revived. And here, after 7 seconds of evolution, they're seeing energies that are comparable to what we see in nature. So of order, a beta of energy injected in this outflowing material over the course of several seconds after the explosion. So both of these are great examples of the ability now of people to simulate and reproduce quark-club supernova explosions. Okay. Yeah, so we have, as I said before, as I showed you a movie of, also have some 3D simulations. They don't blow up, but I'll just show you something about them anyways. So this is the shock radius evolution for these simulations. We have 8 in total, exploring different aspects. But in all cases, the shock goes out, stalls, comes back, and then doesn't succeed in exploding. But there's lots of interesting stuff that happens. And so I'm going to talk about just one of those things right now. So the progenitor perturbations, but there are other interesting things happening as well. So here is a slice through a 3D simulation of a progenitor star before collapse. And you can see that it's not spherically symmetric. And so there are lots of perturbations and multidimensional structures in the star at the point of collapse. And so this area right here that you see has lots of large velocities is the silicon shell that's burning the last bit of silicon and adding to the iron core. So there's, like over here, for example, there's 10% silicon. There's some silicon here. It's just the final burning stages of the silicon. Most of it's iron. But that burning of the silicon is releasing a lot of energy. The fluid is convecting, it's moving really fast, and it's making these simulations multidimensional. We don't exactly use that progenitor, but what we do is we do put some of these perturbations into the silicon shell in some of our 3D simulations, and we can see that the shock evolution is qualitatively different in these simulations that have the pre-supernova perturbations, so these red color simulations. There's a lot more turbulence. So this is a measure of the turbulence. The perturbations that are in the silicon shell to start with allow the turbulence to develop much more rapidly when you undergo the core collapse. And this turbulence, of course, helps you re-energize your shock. And so it doesn't work here, but it is quantitatively closer to exploding than the simulation without the perturbations. And we'll just see that movie here. On the left is a simulation without perturbations, and on the right is a simulation with perturbations. And they're in the silicon shell, so they only actually reach the iron core starting about now, and now you can kind of see the difference between these simulations. The turbulence, there's a lot more turbulence, the shocks are bigger, and eventually they both fail. But for a while there, it was closer to explosion. And one thing about this is you can see it in the gravitational waves. So when these perturbations accrete through the shock and give all this increased turbulence in the gain region, that turbulent material settles onto the protoneutron star and excites the protoneutron star and gives rise to the emission of gravitational waves. So this is a gravitational wave spectrogram. So it's frequency versus time, and the color is the power. So how much energy there is in the gravitational waves at that frequency at some time. And you can see here right around 200 seconds, this is when the perturbations are accreting in. And when that extra turbulent material sets on to the protoneutron star, it gives this burst of gravitational waves. You can see it here in the raw power as well. Okay, so any questions about anything up to now?
I have one. I wanted to ask in this, when you had these perturbations in the silicon shell, then they also affected the way SASI eventually would proceed. It was not visible from your simulation, but you are also changing the size of the cavity, right?
That's right, yeah, because I mean, since the shock is bigger, we can maybe see it here. Yeah, so there is still, so here the shock is bigger, and so the SASI is different. And actually, in the movie, you see SASI in the blue simulation, which is kind of here, but you don't see it in the red simulation. The red simulation doesn't go as far as well. There are phases of SASI. So this feature right here in the shock radius evolution is preceded by a SASI phase. So there's a SASI phase here, and then there's a shock expansion when the SASI stops. It's not so obvious from this plot, but there is still SASI, but this is after the perturbations have already accreted in. I mean, it is true that the ability for the SASE to grow depends on how much convection you have versus how much material you're accreting. So
Yeah.
I mean, there's this chi ratio, and if essentially if your seed perturbations can become convective fast enough before it convects out of the gain region, then this will hurt the development of SASE. Because that's essentially what's happening here in these early times.
Thanks.
Can I just ask a question, Chris Pethick here? How different are the ways that transport of neutrinos is treated in the various codes you compared?
Yeah, they're in all of these 6 different codes. There's a wide variety. So the first one is like a flux limited diffusion almost. This IDSA, they're the green one. So flux limited diffusion. This one is a full Boltzmann transport. Flash and Fornax and GR1D are moment-based schemes, so analytic closures on 2 moments. And Vertex is a variable Eddington factor, so a model closure 2-moment scheme. So a wide variety of neutrino transport mechanisms, although they're all transport. None are leakage or anything like this, but a wide variety.
So what do you conclude? How well do you need to do the transport?
Yeah, I mean, I conclude from this that the full Boltzmann transport is for at least getting the right dynamics correct, that I think full Boltzmann transport is a bit overkill. That's what I think. I don't think we need that. Yeah.
Okay.
Then if you really want to get the neutrino signal precisely, I think there are a lot of other uncertainties in like interaction rates that are larger than the uncertainties that arise due to a 2-moment scheme. As in quark lab supernova, for sure. I mean, in mergers, it's a different story, because I think the moment-based schemes there are less suited for the geometry. Yeah.
Okay, thanks.
Okay, anything else? Okay, so next, let me talk about quarks in supernova. So this is QCD phase diagram. Normal nuclei are down here, so at a nuclear saturation density and 0 temperature. In supernova, our densities are several times nuclear saturation density, so kind of in this regime here. And they're hot, so kind of up here. And then cold neutron stars are way up here. They have much higher central densities than normal nuclei, but they're also cold, so the T equals 0. So supernova do kind of probe this unique region here. And it's very uncertain, nuclear physics, of course. And one question that one can ask is, what would happen if you did have deconfined quarks or something like a mixed phase at supernova conditions? And so this particular diagram here doesn't really allow for that. It's just one I found on the internet. But we don't really have this mixed phase until really high densities that you don't really get in supernova. But nonetheless, it's an interesting question to ask. And so if you have such an equation of state, you can make a mass radius relationship curve for them. So each of these lines is individual neutron stars that have a particular mass and a particular radius. The set of curves here is parameterized by the entropy. So a cold neutron star would, even this light blue one is hot. So a cold neutron star would look the same up here, but then it would come down and it would then go out here at really low masses. It would start to become big. But these hot neutron stars have lots of thermal support, and so they are much bigger. And you can see here, this is a quark equation of state. You can see kind of this, what's called this third family. So here is a point where if you increase the density a little bit, you get a configuration that's not stable. And so it'll collapse and transition over to this configuration. And this phase transition is what we talk about when we talk about quark-hadron phase transitions. And not every equation of state would give this, but some equations of state do. For even these higher entropy stars, you have a slightly different situation. You undergo the transition up here, but there is no more stable state. And so you just collapse to a black hole. So all these states are unstable because you don't have a mass to match the state. Okay, so Shuai, who is a postdoc here at the OKC, took one of these equations of state and wanted to know what would happen in a multi-dimensional simulation. So this has been studied before in 1D, and it's known that this phase transition in some equations of state causes the supernova to explode. And so the transition from the hadron star to the quark star releases a bunch of gravitational bonding energy, and that energy can lead to an explosion. And this happens here after about 300 milliseconds. The central density goes up, it transitions, and then you have a second bounce phase. And this gives a burst in neutrinos, because now this new supernova shock, there's a movie here. This new supernova shock heats up the material, and it causes the material to re-leptonize, and you get a burst in antineutrinos. So here's the transition happening, the quark phase transition shock launching, and then blowing up the star, overtaking that supernova shock pretty quickly, and then leading to an explosion. I'll just let it play again, and then we'll go on. So this is the shock, and then very quickly it's going to overtake the rest of the shock. What's interesting about this is, so it's done in multi-D, and so for the first time we were able to make an estimate of what the gravitational waves from this would look like. And so the protoneutron star convection zone that's in the compact star before it undergoes the second collapse, or as it's undergoing that second collapse, really gives this huge burst of gravitational waves. And so it's short, it's only a few, 10 milliseconds long, less than that, but very strong and really high frequency gravitational waves from this phase transition. The red in all these figures is the equivalent equation of state without phase transition, so without any quarks. And then the spectrogram, again, this time the strength or the strain as a function of frequency over the entire simulation, which is the blue and the orange one, and then just at select times. So everything prior to the second collapse, that's green, and then just the 10 milliseconds right at that second collapse. So this here is that strong, loud, high frequency emission happening during the second bounce. That would really tell us, that something has happened. Some quark transition has happened. There's also a potential neutrino signal from it as well. So I mentioned there's a burst of neutrinos. Shuai took a different equation of state. Yeah, so caveat that what you just saw was an equation of state without a maximum mass above 2 solar masses. So it was below 2 solar masses. More modern quark equations of state, it's hard to get an explosion and a maximum mass above 2 solar masses. But this particular equation of state here has a maximum mass above 2 solar masses, but it doesn't lead to an explosion during the transition. Rather, you get some other interesting physics. So this is central density again. You have the transition happening. It doesn't explode, but then the extra energy doesn't go into blowing up the star. It just sits there and oscillates. So the central density oscillates, and then also shock radius oscillates, and the neutrinos oscillate. So you get an oscillating neutrino signal coming from the quark transition. And then at some later time, a couple 100 milliseconds or a second later, the proto-compact star collapses to a black hole, because it hasn't blown up, so it's still accreting material, and so it eventually will collapse to a black hole. But this intermediate kind of interesting phase in the neutrinos prior to black hole formation tells you that a phase transition happened along the way to black hole formation. So again, another kind of obvious signature that something has happened. Okay, any questions about the quark stuff?
Can I ask, which equations of state did you use?
Yeah, so this is both of these equations of state are based on the Shen equation of state. So this is the TM1 relativistic mean field approximation equation of state. And then with a MIT bag model quark at high densities with different constants, and then some mixture phase in between, so some hybrid mixture in between.
That you get by a Maxwell construction or?
Yeah, I'm not sure the exact details, but something like that, yeah.
Uh-huh.
Yeah, so it's hard. I mean, for supernova, we need the full temperature dependence and the full density and YE range, and so it's harder. We can't just take some cold equation of state off the shelf and use it in supernova. Mm. So there's not as many options available for us as might exist out there. But there are more nowadays. I mean, they're growing, the number of equations of state available.
I also have a question. So when you in the gravitational wave signal where you have those large amplitude modulations, up to which distance would this feature be visible?
Yeah, so here, this is the signal at 10 kiloparsecs, and this is the advanced LIGO noise curve. They're 2D simulations, so maybe if in 3D you would expect these to come down by a factor of a few or maybe 10. But if you take these amplitudes as they are, they're essentially detectable in the galaxy. So it's not, I mean, since the noise rises so fast with frequency, even though it's this really strong signal, it's not, the signal to noise isn't that much bigger.
I see. And then for the neutrinos in the old papers with 1D simulations, they were predicting this second burst, which you also have. But in addition, in multi-D, you have also these other like wiggles in the signal, but they are occurring at very early times. Did I understand this correctly?
It's a little different. So this one is like the original,
yeah,
where it has an explosion. And so you have an explosion and you launch it and you completely stop accretion. And you get this burst from the shock moving through the dense material and heating it up. These oscillations are happening because the shock, it doesn't explode. And so here you can see the shock radius. It goes out a little bit, but it's not able to explode. There's not enough energy released in the transition in order to cause an explosion. But there's some energy, but it's essentially trapped there. You have all this, you have this extra released energy, and it initially it's kinetic energy. It's not heat yet. It hasn't thermalized. It's not exploding, so it just sits there and oscillates for 20 milliseconds or so before it dissipates. And so that oscillation just gives rise to the oscillating neutrino signal. There's still the antineutrino burst, but then it's just followed by an oscillating signal.
I see. Thanks. And we could have also this kind of transitions in neutron star mergers, quark-hadron transitions, right?
Yeah, for sure. Yeah, and there are papers that have explored this in merger remnants.
Thanks.
Okay, so I'll just quickly talk about this. So as I said, yeah, there's lots of equations of state out there, and we use some of them in our simulations. They're all very different in terms of how they describe the properties of nuclear matter, and all the parameters of interest are all different in all of these that you see here. So Andre Schneider has developed kind of a framework for studying equation of state effects in supernova. And so he has 100 equations of state where he varies all of these 8 parameters. These he keeps fixed, but these other 8 parameters he varies, and then he sees what effect they have. Here is just their effect on cold neutron star matter. So changing this pressure at high densities changes the maximum mass of your neutron stars. Changing the symmetry energy changes the radius of the neutron stars. The incompressibility. Changing the symmetry energy changes the low density behavior. And then changing the effective mass, which is a proxy for thermal effects, doesn't really do anything to cold neutron stars because they're cold. There's very little temperature dependence. In supernova, the situation is completely different. And so these first 6 parameters actually have a very small effect on the early thermodynamics in a quark-collapsed supernova. But since it's so hot, this effective mass actually has a big effect. And so one thing Andre showed was as you vary the effective mass from something like 0.6 up to 1, you can get non-explode, these are 3D simulations that don't explode. But then as you increase the effective mass, the neutrino heating goes up, you get more turbulence, and you can get explosions. So the idea is the high effective mass gives low thermal pressure, and this causes the protoneutron star to become more compact. And a more compact neutron star gives hotter neutrinos and stronger heating, and that heating drives more turbulence and gives you an explosion. So that's the idea here. And a lot of the other parameters, as I said, that Andre explored, don't really have an effect on the thermodynamics. Here's another example from Oliver's work, a master's student. Again, high effective mass explodes early. This is a 2D simulation. A lower effective mass explodes, but it's very late, and then this lowest effective mass doesn't explode. And again, you can see the heating here. The green one has the least heating, orange a little more heating, blue a little more heating. So it's that connection between the protoneutron star's radius and the neutrino heating that causes this early explosion. And then it also impacts the gravitational waves. And so this more compact protoneutron star has a higher characteristic frequency. And so the gravitational waves that come off of it are higher frequency. And so bluish colors are high effective mass, orange colors are the medium effective mass, and green is the lowest effective mass. And so these are 3 spectrograms on top of each other now. Okay. Any quick questions about that?
Yeah, maybe one quick question. Can you say what effective mass means in the context of a quark-collapsed supernova?
Yeah, so I mean, it's more in the context of the equation of state, and so it is what is the easiest way to say it? Essentially, how the particles respond to an acceleration or a force.
I see. Okay.
And so it has this consequence that the thermal pressure, so the pressure that comes from the internal energy, or from the motion of the particles, goes like 1 over the effective mass. So low effective masses, the particles have a low mass, and so a particular amount of energy can accelerate it more. Mm-hmm. A particular force can accelerate it more and give larger thermal pressures.
I see. Thank
so
you.
it puffs up the neutron star. So these low effective masses have high thermal pressures, and it keeps the neutron star puffed up rather than contracted.
Thanks.
That's because you're keeping the entropy density fixed, or I'm just trying to. Because the heat content or the specific heat goes like the effective mass times the temperature, so the energy goes like the effective mass times the temperature squared, and yeah, so that would say that it goes like the entropy density squared divided by the effective mass. So if you compare things, fix the entropy density.
Okay.
The argument works, doesn't it?
Perhaps.
Okay, we can talk about it later.
Yeah, okay. Okay, so let's talk about neutrinos some. Okay, so I had this figure about neutrinos here on the left from 87A, and they arrive, before the photons do. So the neutrinos are emitted in the first tens of seconds. The shock is launched then, but it has to propagate through the star before it can give rise to photons that will travel towards us. And so that time can be hours, like it was in 87A, or it can be days for a red supergiant. And since the neutrinos arrive first, then there's the potential to use them to tell us about what to expect from the photon emission, and let us, get as much from this event as possible in the case of a galactic supernova. So this shock breakout is very short in time. It'd be really nice to see it because we don't usually see it. It's usually the first emission that comes from a supernova, so we usually miss it because we don't know to expect it. One of the things is pointing. So neutrinos coming from a supernova, some of the neutrinos interact in water shrink-off detectors like Super K, and they tell us where the supernova came from. So some of the interactions maintain some of the original neutrinos momenta. We would like to know if we can see how far away it is to get the distance estimate to the supernova from the neutrinos alone. And that can help then tell observers it is 3 kiloparsecs away, really close, or it's 50 kiloparsecs away, LMC. So this can help them plan their strategy. So here is the luminosity for 150 different progenitors from supernova. And the problem is you can't really use supernova as a neutrino, as a standard candle, because the neutrinos, they have a different luminosity from different progenitors. If it was a standard candle, you could just like we do for type 1a, you could just get the distance by seeing how bright it is. We can't quite do that, but we can almost do it. And so this is what we're exploring here. Again, mostly Erin and her master student. So here I plot the number of neutrinos in the first 50 milliseconds of the supernova. So only this first little bit, none of this later stuff. In ice cube detector versus the distance away. So this is just a 1/r² plot. But you can see the spread. If you see 10,000 neutrinos, then it could be one of these purple stars at 9 or 8.5 kiloparsecs, or it could be one of these yellow stars at 11 kiloparsecs. So we would like to get it better than that. I mean, this is not too bad, like 10 plus or minus 2, 20%, that's not bad. We would like to do even better if we could. And if you can somehow figure out what this color is, if you can have a measure of this color, then that will allow you to pinpoint this down a little more precisely. And this color is this F delta parameter, and this is what we wanted to see. This is from Haruchi in 2017. We want to see how well can we measure this parameter. And so this is it for all these 150 different stars. And the error bars are the typical value that we can measure it at. So for example, for these yellow stars with high F delta, we can measure it, put 3.5 plus or minus 0.1 or 0.2. So we can do not bad job. And then also, as you can see here, there's this essentially this one-to-one mapping with this parameter that you can measure from the neutrinos alone. It's just the ratio of the number of events in one time window to the ratio or to the number of events in another time window. So you can measure it easily, but it has this one-to-one mapping with this compactness, which tells you something about the star. It tells you the structure of the star during collapse. Yeah, okay, so then with this, we measure this F delta. We know if it's yellow or pink or purple or orange. And then we can go back here and determine the distance even better with the galactic supernova. So how well can we do? For ice cube in blue, at a typical galactic distance of 10 kiloparsecs, we can estimate the distance with an error of about 5%. So better than that 20% just from not knowing anything about the explosion or the star, down to 5%. And Hyper-K will do something similar errors. It'll do a lot better at large distances because there's no noise. And then, current or near future detectors like Super-K or Juno is more like a 10% distance error. Okay. Oh yeah, and then this is much more speculative. Whether you can then say what the zero-age main sequence mass of the star was. So if you can measure an F delta 2, you can essentially say that it doesn't come from any of these really high mass stars because they don't predict an F delta that high. So you can kind of, with lots of caveats involved, quickly say with just neutrinos from the very beginning of the explosion, whether or not it's a less than 12 solar mass star or more than 12 solar mass star. It's kind of the limits, but this is more speculative. Okay, I think I'm out of time for this, and so maybe I'll just stop here and not talk about this parameterized explosion model unless someone is particularly interested. Yeah.
Okay, thank you very much, Evan. This was a very nice talk.
Thanks. Yeah, sorry for rushing there at the end. But
you still had like 5 minutes, so if you want to use these 5 minutes to talk about something.
Well, if someone is interested in that, they can ask. But I would rather take questions about
other questions.
Yeah.
So let me start with one question. So you mentioned this QCD phase transition, and this will basically also lead to a second neutrino peak. Is this something that would be visible in neutrino telescopes as well?
Yeah, so that these oscillations we estimated would be visible in something like ice cube at 10 kiloparsecs. So we should be, so these are counts in ice cube in thousands per millisecond. And the background, as you know, the background rate is also of order thousands per millisecond. And so this is of order, the oscillation in these signals is of order the background rate. So this should be visible in ice cube for a 10 kiloparsec supernova. Like resolving the individual oscillations, not just the peak.
I see. So the characteristic feature would be the oscillation itself, not the peak that you observe. Okay.
Yeah, I mean, for these guys. So for these ones here, they undergo this oscillation. For more compact stars, they just go directly to a black hole. You don't have this oscillation phase. And then for the really low mass stars, you really don't have a strong transition. So we go back to this one here. It's these ones where the gravitational, for a fixed baryonic mass, which is not exactly this plot, transitioning from here to here releases a huge amount of gravitational binding energy. Down here, you don't release very much at all. And here, there's just goes straight to a black hole.
Irene, you have a question?
Yeah, so I wanted to ask you about the last plot that you were showing for the zero-age mass sequence. What is so special about the 12 solar masses?
Nothing really. I mean, here in this figure, it looks like this because of the 2 and 2.5. But essentially, it's stars that are less than 12 solar masses, which is here, have potentially F deltas that are small. And above 12 solar masses, you don't have small F deltas.
I see. Thanks.
Yeah, I mean, this F delta compactness relation is almost 1-to-1. And so essentially these really low F delta stars have the lowest compactness, and compactness is, I hate saying this, but to first order, or to 0th order, it is linear in 0-age main sequence mass.
Yeah. Thanks.
Are there further questions? Okay, this doesn't seem to be the case. Then thank you very much, Evan, for this very nice talk.
Yeah, thanks again.
All right. Then thanks for joining us today, and see you soon. Bye-bye.
Bye.
Thanks.
Thank you very much. Bye.